Okay, so let's move to a system that is doable using the Lagrangian formalism, but much more difficult using F equals ma. So let's say that's the y direction and this is the x direction. We have x and y coordinates, and we have a block of mass m2 on a frictionless surface attached to a ring, circular ring, but let's make this massless. Here's a circular loop, so it's a hollow loop, and inside of this little tube we put an object of mass, some object of mass, a little marble, if you will, of mass. Let's say m1, and we are this is sort of a table, and so there's just the vertical direction. Gravity acts downward, so there's an m1 g force acting downward always, right? So it's always downward, but the normal force from the loop is different. So here the normal force is pointing that way, at this point it points that way, at this point it points downwards. So that makes it very complicated. So let's say that the radius of this loop is, of the circular loop, is r, and then we attach this, so the mass of this ring is negligible, and this thing is sort of a rigid rod. Its mass is also negligible. So the only things of mass are m1 and m2, the marble and the block. So this object is, right, it's falling due to gravity, but it has to obey the constraint that it lives inside that tube. So if we have some angle here, theta, that angle's changing. Okay, so if we think in terms of F equals ma, we have the normal force, we have m2g downwards, we have the constraint force here, that's like a tension pulling this object. We have what we saw before here, so that looks like a very complicated system, but using Lagrangians, all we have to do is find kinetic and potential, and let's write them in terms of certain coordinates. So if we look at this object, it has a y value, so the center of mass is there, it's some constant, let's just call it, right, y equals y naught. That value is fixed, so this object could move this way or that way, but it's not going to move upwards. Its x position, so if this object, if this point here is x, let's say, this point is x, then this object is x plus some constant, whatever this length is. So constants don't really matter, but it's x plus some constant, like that. Then this is the coordinates for the object of mass m2, and for the object of mass m1, the marble, we have a coordinate which is x, but we have, right, the object is over here, so its x value is here, so we have x plus this part, which is r sine of this angle theta. That angle is changing. That's its x position, and its y position, right, its height. If this is ground level, then its height is here, then it's just r minus this, so that's r minus r cosine of the angle theta. Okay, so that's all we need to be able to find the Lagrangian, which is the kinetic minus the potential. And so we have the kinetic energy of the object of mass m2 is simply m2 over 2 times its speed squared, which is just the only thing that's changing there that can change is the x value. So we have an x dot squared plus the kinetic energy of this object, So we have an m1 over 2, and now we have to square, right, we have to take, we see that both the x and the y values can change, and so we have an x dot squared plus y dot squared, and so the x dot term looks like x dot plus r, we have a theta dot, right? The derivative of this is cosine theta theta dot, so we have a cosine theta there. We have to square the x, plus we square the y dot, right? So this is a derivative here. Nothing from this. From this term we get an r theta dot sine of theta, and we square that, and so we have the kinetic energy, and then we add to that the minus the potential, and so that is minus the potential energy is only due to this object being at some height. Right here is the height, so we have a minus m1g times r times 1 minus cosine theta. Okay, so that's all the work we needed to figure this out. Notice that we sort of bypass all the constraints, the tension forces and the force of the normal force here on the marble, and we can get the equations of motion from this. So let's do dl by dx, and we can see that that's equal to 0. And then we have the counterpart of that is dl by dx dot, which is m2x dot plus m1 x dot plus m1r theta dot cosine of theta. And this has to actually be a constant, right? This is the momentum in the x direction. If we take a d by dt of dl by dx dot, this is going to be equal to 0, because this quantity is a constant, and so we get an m2x double dot plus m1x double dot plus an m1r theta double dot cosine theta minus m1r theta dot squared, because we were taking the derivative of this, so we get a sine of theta, and that has to be equal to 0. So now we have the other coordinate to deal with, and so that gives us, so we are dealing with dl by d theta, and that is minus m1 r x dot theta dot sine of theta minus m1gr sine of theta, and the dl by d theta dot is m1 r squared theta dot plus m1 r x dot cosine of theta. And so, of course, we now have to take the time derivative of this term and set it equal to that. This is dl by d theta dot, and that is m1 r squared theta double dot plus m1 r x double dot cosine of theta. Now we have to take the time derivative of this term, So we get a minus m1 r x dot. We pull out theta dot and we turn the cosine into a sine. So it looks like that. And so this is equal to that. And so we can simplify it. We can divide by r, bring this term to the other side. And so our equation looks like r theta double dot plus x double dot cosine theta plus g sine theta equals to 0. When I think about trying to get this from f equals ma, very difficult to do that. So the Lagrangian formalism allows us to do this in a very simple way once we can figure out the coordinates that allow us to get kinetic and potential energy.